Hello and welcome to European Researchers Night live from Teknikens Hus here in Luleå. This event is taking place all across Europe from countries like Iceland and Montenegro. The purpose of this event is to promote research among the public and also to inspire young people to study science and research at higher education. Last year, this event attracted over 2 million viewers. I wonder if we will see that many today. Today, we have our researchers with us, and the theme for this year is Living Sustainably in the Future. With the motto, researchers are ordinary people with extraordinary lives, I would like to introduce you to our speakers today. We have Zahra Monfared and Marcelo Takehara. We also have Karina Tommik and Tarun Bansal. And of course, we have Björn Lindqvist, who will talk about robots. So now we have Marcelo and Zahra with us today. So welcome, and please take the stage.
Hello, good morning.
Good morning.
Yes.
Welcome.
Thank you. We just check. How is the share screen?
Yes.
It's working, right?
Yes, it is.
Perfect. Right. Thank you, Heather. Good morning, everyone. Always nice to be here in the Research Week. As you said, my name is Marcelo.
Zahra,
with us. We are going to present a bit of what we doing here in LTU as researchers and why did we choose our research topic and also the place. We work both as PhD students at energy engineering here at LTU, and we are talking about from different aspects of energy, from biofuel production to CO2 capture, batteries, and some new or future perspectives. This is our big group. All of them are PhD students here, our colleagues. We have maybe 10 or maybe even more different countries represented here. Our seniors, professors, postdocs, and from different areas. We're not going to say all the names, but we are a big group here at Luleå Technical University. I will introduce a bit myself. As I said, my name is Marcelo. I came from Brazil, specifically from São Paulo city, where I studied. I did my bachelor there in mechanical engineer. After this, I did some work in industries, mainly with combustion systems. So going to visit some plants, industrial plants, and doing some technical consulting about process, heating process, combustion process, and so on. After a while, I decided to go to Italy, not only to eat some nice pasta, pizza, and wine, but also to do a master in energy engineering. That's where I started this more go towards research. So I worked a bit in industry, but after a while, we decided to, okay, let's try to go back to research, to academia. So we decided to do this master in Milan in energy engineering. And after this, we took this position I took this position in Luleå. This is not representing my research specifically, but it represents the environment here that's really nice. But also still working with some combustion system that we can see in this short video. So this is what I'm currently doing in our lab, and that I'm going to explain a bit later on how we can relate this to energy engineering. We can now go to Zahra.
Yeah, okay. I'm Zahra. I come from Iran, the capital, Tehran, as you can see the crowded picture, the crowded city. And there I got my bachelor in mechanical engineering. And as they say in my country, mechanical engineering was called the mother of all engineering programs. So after that, we had some freedom to choose whatever subject of research we wanted. And then I was really interested in renewable energies because at that time we knew that the future is for green energy, renewable energy. And then I decided to move to Germany and to Ulm city. You can see the representative of that city is the tallest church, cathedral. Mm-hmm. Called Münster. There I got my master in energy science and technology. And the interesting thing was that at that time I just knew about solar energy, wind energy, these kind of general topics that we have heard from renewable energies. But in my master, I also got to know more about fuel cells, batteries, and other sorts of renewable energy capture and storage. So I shifted a little bit to batteries and fuel cells, but the material of these kind of storage devices. And then after that, we moved to Sweden, to this nice city that Marcelo also said. And I'm really quite fond of the winter here. You can see different activities we do. And yeah, it's not representative what I do because I'm mainly now into simulation of biomass in steel industry that we can talk about a little bit later. But yeah, that's it. We can.
Yeah. So yeah, why did we choose energy engineering in the end? So I will not go in much details, but what we can say at least is that energy is this graph, for example, is the energy supply from the International Energy Agency. And you can see that the energy supply is increasing towards the year and it's going to increase in the future. But what we're seeing now is a bit of this transition to clean energy. This is what people are saying, that was in the news, how we go to clean energy, how we can go to sustainable. This is the topic of the research week, right? And how we can use hydro, how we can use solar, wind energy, for example. And this is what we need to talk about. We can say easily, we need to stop fossil fuel usage, but we need to decide how and which ways we can do that. You can see from the news as well, more specifically here in the north of Sweden, a lot of investment, a lot of research going on about fossil-free steel, for example, production, using hydrogen. So we have a lot of projects going on with hydrogen production, hydrogen storage. We have our professor here, Heather Jacksic, doing interviews, doing live conference, presenting also what we are doing and what university is trying to also to help in this direction. And this is the fun and the excitement of energy engineering. There's always something new. For example, it's important that we go towards clean energy in sustainable usage of energy, but we need to see how it is done in practice. This is what I studied a bit, or probably Zahra as well, doing the master. But here, as researchers, we can do things a bit more focused on this direction. So mainly what we see in our group is how to do this transition towards clean energy, but we do that in a big group, including from fundamentals of how to produce biofuels, how to storage them, how to use biomaterials, for example, to increase efficiency in some kind of process. But we also need to see the other end, how to say or how to communicate this to a national level, to create policies. So we need to use, okay, biofuels, but we need also support from government or make this process achieve other levels. And this is what we do it here. And we can go from fundamental part, as I said. So mainly this part, what we both here are doing. So we're looking specific for myself. I'm doing research involving gasification. That is how to produce gas, a syngas or a synthetic gas. But this is really focusing in fundamental parts. We have another group here using, for example, energy system and policies. Another group studying energy efficiency, and other group studying more batteries and CO2 capture and storage area.
And the interesting thing about all these groups is that we all are in somehow close contact with the big industries in the field that we're working. So we have sometimes meetings with them, and we exactly know how our work is going to be used in that industry. So this is also interesting, especially also for me. And it is like when we went to the company this year to just talk about our research, they were saying, okay, yeah, maybe it takes a lot of time to get completely green in sense of biomass and production of steel. But it's a good money and time that we are spending, so that after maybe several years that the customer comes to us and wants a pure green metal, then we have everything done and we can give them the products. And that's what we do here.
Right, then I think here we go a bit quick. This is just representing what it's different areas that we have here in our group. My area is this one, is conversion technologies. So what I do here is try to convert biomass into a product that's useful for industry or for energy purpose. In my case, it's a syngas that we call. But then we can use same application, same research to also industrial heating and heat and power plants, for example. We have a lot of also in other bioproducts, biofuels like charcoal, bio-oil, even maybe methanol, and then also in these days we're talking about of hydrogen. We can also study some conversion ways from biomass to hydrogen. It's also we studied here. Something else here? No. Other group that we have is energy systems. So in the same way that we are studying how to produce these biofuels, how to introduce them in industries or in our lives, we are also studying how to increase the efficiency of the current process. And then this is what one of the groups does here. So we need to increase efficiency to save any fuel consumption that we have. We are also studying energy efficiency in buildings, not only in industries. And the other group, it's studying more in system analysis, how to do this in a national level or a municipal level. If we introduce, for example, a new biorefinery, for example, to produce biofuel for, I don't know, maybe airplanes. What is the position, or where's the location, best location that this plant can have, and how to do a model of what is going to affect the other industries or the other actors in the energy area. So this is what this other group does.
Yeah, and also in other aspects, when we get into renewable energy, the heart of any renewable energy system, either the energy is got from solar or the wind or anything else, is the battery and the storage, because we need to store energy and then use it later or integrate it into the system. But for storing now, the most popular one is lithium-ion batteries that you might know when you have it on your laptops or mobile phones. But what they really now use is like the stacks and the big, more like big, larger units of lithium-ion batteries, and they can use it. For example, this photo here that you can see. This is 55% charge of a whole battery stack in Tesla, and you can see the position of the batteries. It's like it's on the chassis of Tesla, yeah. And yeah, now it's really the art and the edge of science on lithium-ion batteries, because their lifetime and their efficiency is really important these days. And you can see this is how chemical engineering and chemistry is also related to our division and energy engineering, because the fundamental of battery in the lithium-ion batteries is the chemistry that's happening, and then the electricity that you get from that chemical reaction. And also we have a group that they work also specifically on the green electrolyte, the green anode, green cathode, so that all the components of that lithium-ion battery is also obtained via green energy. And, yeah.
Yes, so now we're going to do a small virtual visit in our lab. Hopefully you can see the video. Yeah, this is the first video. This is where we do the chemistry of our research. So here we do fuel characterization, for example. We do some studies in carbon, in CO2 capture, in maybe ionic liquids or batteries, as Zahra was saying.
Characterization.
This is what we call the clean lab. Now we're going to see. Oops. Let me try to change. Yes. This one is the big lab, so it's a bit more. I will not say dirty. It's a bit more stuff with big reactors. So we have here the main 4 reactors that we can see. One, it's Auger Reactor for biomass pyrolysis, a drop tube furnace. Then we have a pellet boiler, more like a commercial residential pellet boiler, where we do some studies in clean gas, cleaning of the flue gases. And then this is a flame reactor, where we can visualize what happens inside a combustion chamber or in a gasification process. If we enter the lab, we're going to look like a bit messy, but I don't think we can clean more than this.
No, it's very dedicated.
This what, yeah, exactly. So here we have all of our biomass. We can prepare them, characterize them. Then we can go for the first reactor. It's this reactor, for example. We call it Auger Reactor. It's basically, we can feed biomass from this hopper here. And this is a screw feeder where we can preheat it. And then we can produce charcoal in different ways and using different process. So here we basically investigate how to produce charcoal using biomass. So we can relate charcoal, the same thing that you use in your barbecue or for cooking purpose. But this also we can do for substitution in industries. For example, they use a lot of coal for producing iron, for producing or maybe heating for industries. And we studied a lot how to use, instead of coal, a fossil fuel, how to use charcoal or biochar. And then this, we need to produce this biochar with specific characteristics depending from the purpose. I think this is what also Zahra is doing in her research. try to go to the other part of the lab. This is the drop tube furnace, so we can study also similar things, how to produce different biochar or even syngas. Now the video is a bit going, yes, then we go. Maybe we can stop the audio. Yeah, this is the, I will just stop here. What we saw there is this big reactor, we call the Flame Reactor. And we inject biomass from the top, for example, and then we can see what happens inside. So you have some nice cameras positioned, and then we can see the flame or the combustion or the reacting conditions inside this reactor. And this is what I do, is try to produce syngas with a more efficient way. If we can also see this with small particles in other conditions, also using cameras and optical access reactors. What else? Yeah, then I think we are going to end just talking a bit about how the education is here.
Yeah, it's the name of the program that if you want to join our energy group, you can apply for it. That is a master program in sustainable energy engineering. As you can see, there are different batches like bioenergy, electricity, and fuels. Well, yeah. Mm-hmm. Sorry, my Swedish is not good, so that's why. Yeah, but since we wanted you to see the main names of the courses, it's good to see them in Swedish. And yeah, about smart energy. And during these studies, as far as we have experience here, we have really a good atmosphere. It's really friendly, and the PhD students, the seniors, they're really accessible and they're helpful. And somehow you are really free in choosing your field of interest. So yeah, and since the future is for energy, you're welcome to join our group. And we are here in the corridor if you have any questions or if you want to talk about any specific topic for your future studies. Yeah, welcome to join us.
Yes.
All right. Thank you for that interesting presentation. I was going to ask if the students could drop by and see what you're doing. There's also high school students that maybe are watching this online, and they probably don't have a chance to come and meet with you in person. But I wonder if you have an email address or somewhere where they can contact you.
Yes, yes.
Maybe that's something we can put in the chat.
Yes, I can put in the chat.
Perfect. Thank you. Thank you. Well, we have our international and exchange students here with us today, and I'm wondering if you have any questions for our researchers. You have a question. Yes, please go ahead. You can come up here, sure. Or you can just say, yeah, that's fine.
Like to know about certain new areas, for example, in maybe using technology like nanotechnology in maybe doing some form of stuff that can provide energy, or I don't know, do they have something like that?
Some kind of nanotechnology. So the question is whether or not you have any kind of nanotechnology that you're working on.
Nanotechnology, that's a...
Yeah, I think the group that I told you about, they're working on the chemistry of lithium-ion batteries or ionic liquid. They're also working in nanoscale because it's working on the membranes, and in membranes you really have like small pores, and the reaction is happening on very small surfaces. So yeah, we have people who have had nanomaterial or nano engineering backgrounds here. Yeah. The new students we have.
Yeah, but maybe I don't know if it's more related with material production, or, and then this is, we have other groups here in our university from material science that they do more specific in this in material science. Here we have this what Zahra told, but not specifically in my area, or I don't know.
Yeah, specifically like nanophysics and nanomaterial. Also, we have another specific group for it.
Yeah.
But here is more industrial and practical. And then I have a question here. How did you become?
Yeah, there's another question. It says, how did you become interested in this research area?
Well, talking about my case, so was a bit, for me, was a bit different because when I studied like mechanical engineering at that time, I didn't maybe think too much on the energy engineering in this biofuels or how to produce syngas in efficient ways. I was maybe more trying to go for a industry career at the time. But then when I started actually working in the field, in the combustion systems, then we could see, okay, this is interesting. So flame for itself, it's interesting when you see something burning, even doing a barbecue, for example. It is nice, right, to see what is happening. This is what, and then you see this in a bigger scale, a really large scale. For example, if you go to see a cement plant, and then this attracted me quite a lot. And at the same time, in industry, we actually don't have that much time to study, to go deep into research. And then maybe I should go back to academia and try to understand a bit more these things. I think this is more or less how I stop in this area.
Okay.
Maybe Zahra has a different.
Yeah, for me,
Yeah.
mechanical engineering at the beginning is somehow the same, but then for me, it's kind of narrowed down because I had some big pictures of renewable energy, and then I just got to know more and more about new stuff like fuel cells, batteries, and now biomass. And then like how I found the topic interesting, I just followed. So it was not really consistent for me. And I think this question is also interesting. Do you have a dream research project?
Dream research
Yeah,
project.
do you have a dream research project?
You can start.
Yeah, actually, if I really want to be like really illusional, it would be for me to optimize the fuel cell cars in sense of cooling and performance and this stuff. And yeah, at the time that I was working on fuel cell, I don't think the governments are really convinced that this is the future. So I had to come out of the field. But that's something interesting if anyone wants to check.
All right. Well, thank you very much. We are just about out of time now. Do you have any last words that you would like to share with our students?
Well, I would say that considering for at least go for higher education or university, and consider research not as like this crazy scientist as we can time to time. Hopefully you're not crazy enough to but it's really important to have people working in research and academia to investigate things. It's easy to see news, we need to go fossil free, or I don't know, some other, but we need to understand how to do that, and how to do these things. We need people, we need researchers studying from really fundamental parts, but also to investigate in a bigger picture. So I think that was my...
Yeah, definitely.
Yeah, okay.
Thank you very much. Well,
you.
we can give a little hand of applause here for those of you who are presenting for us. Thank you. Now we will move on to our next researchers, that is Tarun and Karina. And so there you go.
Yes. Yeah.
Welcome. Hello, how are you today?
We are good. How about you, Heather?
Oh, I'm fine, thanks. All right, are you all set?
Yeah, yes.
You can go ahead and share your screen, and the floor is yours.
Thank you. So it should basically one. Yeah. So, okay. So we are geotechnical engineers. And obviously we work at the Luleå University of Technology at SBN in the group of geotechnical engineering and mining. And as geotechnical engineering is often confused with geology, which is not quite what we do, we decided to first tell you what geotechnical engineering is and how we apply it. So basically, geotechnical engineering has to do everything with soil and building out of soil and using soil to build things. So firstly, we can harvest the soil, for example, mining. For example, even like mining iron ore like you do in Sweden. But often what people don't think about is, for example, in concrete, we use a lot of sand. So where does that sand come from? So we need to harvest this sand. So this is one aspect of geotechnical engineering. Secondly, and I think this is kind of most common application of geotechnical engineering, is we build foundations. So all these beautiful tall buildings in Manhattan need to stand on something. And often the soil underneath is not strong enough to carry this weight of the building. So geotechnical engineers design foundations that distribute the load over this soil, or they even transfer the load into lower layers of the soil that are stronger. And this is what you see on this right side picture, where you have piles that are these kind of concrete columns that transfer the load of the building into deeper layers. What we also do is we use soil to build structures like dams. So often I think when you think about dams, you think about the Hoover Dam, these huge concrete structures, but actually most dams in the world are built of soil, just compacted soil with different properties, so you can stop water from flowing through it. And finally, we also build underground structures like tunnels, and as previously mentioned, also mines. So yeah, everything that has to do with the stability of the ground, we kind of work with. And I'm gonna also like show you some examples of geotechnical engineering, like large scale projects in Sweden. So I'm sure you're all familiar with Slussen in Stockholm. So they're redesigning this bridge and intersection to make it more accessible to pedestrians. And here, as you can see, there's a lot of water around, so it's very challenging to build foundations underwater and trying to keep the water out of the excavation. So you can build these bridge structures. Then also we have Västlänken in Göteborg, where we're bringing the railway into the city. So we have to have these huge excavations in the center of the city with buildings around them. So we don't want to damage the surrounding buildings due to settlement of soil. And the soil in Göteborg is clay. And as you can imagine, clay is very soft. So it is quite difficult to build on top of that. So that's quite challenging. And then also an example from Luleå. This is a Kuststad. This is close to the South Harbor, close to Willys. And this is how it used to look like. And you think, what is this? Well, if you think about it, there are these new beautiful apartment buildings that they built there. And they completely filled this area of sea with soil, so they can build these apartment buildings on top of it. So it's a little bit like what they do in Holland and Amsterdam, where they're trying to reclaim land by putting soil there. So now we would like to show you a little demonstration of kind of what we mean when we talk like we build with soil and we want to improve the soil to take these huge loads of buildings and other structures. So I think we have to stop sharing our screen momentarily so we can show you two little experiments. Okay. So yeah. So firstly, I have this bowl here, with a suspicious white liquid. This is cornstarch.
They cannot see.
Yeah, but like this is cornstarch filled with water, and it has very interesting properties because it behaves like a fluid, like you can see it drips. So it doesn't have very good bearing capacity. You can't really build a building on top of that. So if I take this small pebble and I don't know, so if I take this small pebble and I put it on top of here, I don't know if you saw that, but it sunk. However, if I distribute my load over a wider area, so I use this piece of paper to put on top of here, and then I have this iron ore pebble, and I put this on top, it does not sink, and I think you see that. So now Tarun will also show a small demonstration. And the soil also, if you think about different types of soil, so it can behave really differently. For example, clays are really soft, and even sand, if you think about sand by the sea, like you can sometimes sink into it, so it would be difficult to build on that. So this is why we need to improve the soil, and Tarun will show that.
Okay, guys, so this is sand, and normally we build some structures on the sand. So imagine if you are standing on a beach and try to build some structure with sand and you want to rest something. Can you able to build something with this, just this sand? So what we should do in that structure. So I will show you what we will do. So see, this is an empty box, and I will show what we can do, how to improve the soil with this. So I will gonna use this paper as a reinforcement so that my sand will stay at one place. The other side. No, it's this side.
So now Tarun has put the paper underneath, and now he's putting the sand inside the box.
So I will build different layers with that.
And if you even think about, and now he folded, it's not very well seen, but he folded the edge of the paper over once more. So now you have a sand in between two layers of the paper like that. And now he's adding more sand and another layer of paper. And this is like, if you imagine if he would just pour this bucket of sand into a pile, it would just form kind of a little mountain shape. It wouldn't really, would just crumble and spread.
Now I will going to put the final layer on that.
So Tarun here is using paper, but in real life we obviously wouldn't use paper. So we have things that are called geogrids that look something like this. They are kind of plastic mesh materials that are quite hard, like quite rigid. And these can be used to reinforce soil. So
now you see this box is filled. And now I'm going to open up it from one side. And you see that it stays. So if you can see from that side, that it stays. And now I'm going to put some load and see if it fails or not. Because if you put something directly on sand, then the slope will fail. But in this case, it stays. So this is basically the function of the reinforcement. And I can try to put this bucket as well on this and see if it still stays. So see, so in this way, we can actually improve the soil. And in real life, we use Geogrid or some other things, some nails or rock bolting, or it depends what the structure require, or some chemical use. So this is one of the illustration that how you can improve the soil with different things. Yeah.
Yeah, so now we're going to go back to our presentation. And this was examples of adding things, kind of layers into the soil or on top of soil. But sometimes we can also mix other materials into soil to change its properties. So now I'm going to talk a little bit about our group. So our group have people from many nationalities, and we're extremely close, and we do many different research projects, from dams to these mesh reinforcements to frozen ground. We also do a lot of teaching. There is a geotechnical engineering program in masters, but also in like master's level, where it's just a 2-year program, and also there is a 5-year program that is taught in Swedish. Now we're going to move to talking a little bit about ourselves. So in my free time, I enjoy being outside. I really enjoy going to the mountains, spending time with my dog, hiking. And after I graduated university as a geotechnical engineer, for a while I was working in a construction company. So the top picture of the tunnel is the first construction project I ever participated in. And the picture in the top right corner is me on my first day at work in the construction company, where I had to be on site. So I was extremely proud to wear that helmet. And then the bottom picture is the last project that I participated in, which is a 12-meter deep excavation in the city center of Tallinn in Estonia. So we had to build these reinforcement walls around this hole in the ground, so the surrounding buildings wouldn't collapse into it. And now there's actually a 10-story building standing over this hole, and the excavation itself is a parking garage. But I couldn't really stay working at the company, because ever since my master's studies, I was really interested in frozen soil, and I really wanted to come back to that. So this is a picture from a small test I did for my master's studies, which shows the freezing process of clay. And then in the top picture, you can see that, okay, you see the gray clay, but you can also see water, frozen water in between the clay layers. So those are ice lenses, and that is one of the main reasons we get kind of frost damages in roads and kind of settlements under buildings, and we're gonna continue talking about that now. Now I let Tarun take over.
Thank you, Karina. So now first I will talk about myself, that where I'm from. So basically I'm from India, and it's my hometown is quite in the north, so it's very close to the Himalayas. And then I did my master's studies in geotechnical engineering from one of the oldest civil engineering colleges. And basically this college was built only for the purpose of design of aqueduct. So aqueduct is basically when a river crosses a canal. So that college was open just so that you can design the aqueduct, and it was opened in 1850. So that's where I did my master's. And during my master's, I got an opportunity to come to Munich for my thesis project, master thesis, in 2016. And then I went back to India and worked in an Australian firm. And then later I come back to Sweden in 2018 to start my PhD. And so what are my my spare time or free time, I like hiking and also like all outdoor activities. So now you guys are wondering that what I'm doing here, because I'm working in a geotech come up so north of Sweden from India. So basically, my hometown is quite close to Himalayas, and Himalayas have some frozen grounds, if you guys are aware of. And basically, there are a lot of slope failures there, and road conditions are not that good. And where can I do good research in frozen ground? So I chose this place because it's a better place to research about frozen ground here. So that's why I choose to come to Sweden. And now I will move towards frozen ground, as I was talking about frozen ground in the recent slide. So you see this picture on the left, that this is you see it's an island in Greenland. So basically, there are two types of ground, that is frozen and unfrozen. And if you see, 24% of the ground in northern hemisphere is covered with this frozen ground, and about 2.2 million people lives there. So what do you think about this frozen ground? And if you see, they are, I mean, in the picture on the right, you see the frozen grounds marked in blue. So here in the Greenland, and then part of Alaska, and then here in Himalayas, and here we have Sweden, and here in the south is Andes, and then it is Antarctica. So basically, due to this climate change, so ground is changing and the ground is melting, and is so many people is living there, and infrastructures are built on this ground. So we have to do something for this, so that these grounds are stable and the climate there is sustainable, and people who are living there stays there. They don't have to move anywhere south, so that I mean, just because the place is not livable anymore. So now I will show you guys some video about that. What do you mean by this frozen ground? And if we go to the frozen ground, so let's see what does this frozen ground means.
Permafrost contains frozen water, which acts like cement, binding loose sediment together. When this ice melts, the ground becomes weak and unstable. Weakened coastlines, compounded by the effects of retreating sea ice, warmer waters, and longer storm seasons, become more vulnerable to erosion. In towns and cities built on permafrost, infrastructure was constructed assuming that the solid foundation of permafrost would not change. The loss of this permafrost can result in shifting and settling of the ground, which can damage or even destroy infrastructure. This disrupts everyday services and costs national economies hundreds of millions due to relocations or increasing cost of repairs. In high altitudes and steep mountain terrain, thawing permafrost increases the risk of rockfalls and landslides, which can trigger additional hazards.
So this is about the permafrost. Basically, permafrost means the ground which stays permanent frozen. So now we see that due to climate change, what are the consequences of this melting permafrost? So now you see, because of the thawing of the ground, there is a coastal erosion on the side. And the guy is looking at how come this big islands come into picture. And now on the side, we see a picture from Russia where a house was built on a frozen ground, but when this ground got melted, the ground become unstable, and then foundation reaches to failure stage, and that's why the house was tilted to one side. And there is another house picture from Russia, and if we see these now, the pictures of road, so even the roads have these cracks. And you guys, when you travel around Sweden, especially in Luleå, you can see some cycle roads where basically you see those cracks on the middle of the ground. And imagine if you are traveling high with your car and you get this kind of undisturbed road, this uneven road. How will you drive safely on this kind of roads? So basically, my research is more focused towards these cracks and this unevenness of the ground. So I will explain a bit more on this, that what is my research. So if you see these pictures, so they are the cracks on the on the pavements, on the roads or cycle roads. So they can happen either on the middle of the road or on the side of the road. So my main research is just to make better this road and make even this road and eliminate this longitudinal cracks. So that's why we study this, so that we can do something for this kind of roads and to make life smoother for the drivers and also the pedestrians and cycle drivers, cycle users. So at LTU, we have our laboratory test setup where we can set up the soil and test the soil for this frozen properties and see that how much is this effect of freezing the ground and thawing the ground. So here we have the setup where we can just test two things at two samples at a time. Unfortunately, I cannot show you the exact laboratory setup in a real practice because then you have to come to laboratory and visit our lab so that I can properly explain this, how this setup works. But in real practice, the testing of this whole soil sampling takes around 18 to 20 days because it requires some reaching of freezing temperature and etc. But here I have some video where I can show you that what is the effect of freezing the soil and how you can see those ice structures in the video. So you see in this video, we will soon start that. Now if you can try to see, the ground is now thaw and stop, and now you see in the middle of this layer, when the freezing is taking place from the bottom, these ice lens layers are building. And because of this ice lens layer building in this sample, basically our whole soil is moving upwards. And this is what happens in real. So if you imagine, so if you see these cracks on the road, so this is what actually happening in the real practice, that under the pavement, when the ground becomes frozen and the freezing starts to take place from the top, these ice lens starts to build. And if you remember from your basic high school, that ice is 9% more, ice has 9% more volume than water if water converts into ice. So this is what happens, that the ground becomes unstable and it has some cracks. So this was about my research, and now Karina will explain about her research.
Yeah, my research focuses specifically on culverts. You might ask, what is the culvert? So if you look at the image on the left, you see this pipe coming out of the road structure. And I'm sure you all seen those. They are built often under roads and railways, and they allow for water to flow from one side of the road to the other. So we can drain and guide away water and we don't get any floods. However, when you introduce a pipe to any sort of structure, it's not just water that gets in there, it's also cold air, and that changes the temperature surrounding this pipe. So when you look at the image on the right, so in that case, if the cold air in the winter can enter the pipe, we will get much deeper frost penetration around the pipe than on the side of the road, because we're exposing this inside soil to the effects of the outside air. And then similar thing to what Tarun described basically happens, because we get deeper frost penetration, a larger volume of soil will be exposed to these freezing temperatures, and we can get even more frost heaving. So this whole pipe can now be pushed up. And this is, you sometimes get these bumps that are going through the whole length of the road. And this is also connected to permafrost engineering and other pipes that are buried in soil, for example, water pipes, or some pipes are designed to transfer air. So all of this, like if you imagine you have this permanently frozen ground, but you have a water pipe in it. So water needs to stay above 0 degrees to keep moving. Therefore, it will be melting this permafrost around it. But as we discussed earlier, that's something we want to maintain. So this is what we really need to focus on. One of the issues is, how do we know what is the temperature inside these pipes and how it will affect the surrounding soil layers? So I know now we have been quite negative about the effects of frost, But actually there are some positive applications of frost, and sometimes we even want to freeze the soil ourselves. So frozen soil is very stable, as we discussed previously in the video. It said that it's like cement. If you can imagine, like building a tunnel through rock would be quite easy. The rock stands up on its own. What if you want to build the tunnel through sand? Like, I'm sure you can all imagine and remember trying to dig a really, really deep hole on the beach when you were little. And that hole always ended up collapsing. We don't want that to happen to our tunnels when we're building them. So what we often do, as you can see in these pictures on the right side, is we freeze the soil around the tunnel we're planning to dig. And then the soil is really hard as a rock, and we can dig out the center and then cover it in concrete. So then the concrete holds it up, and then we can let the soil thaw again. So there are positive applications also. But I think the final thought we want you guys to live with is that there is nothing permanent and that we should expect change. So while we are trying to do our best, and many other researchers around the world are trying to do our best to maintain permafrost, but we need to learn to adapt to change and try to always improve. Yeah, thank you.
Thank you.
Wow, thank you very much. This is very fascinating research for sure. Okay, so we will ask if our audience has any questions. The water? Oh, the weather. The question is the weather a great challenge to your research?
Yes, extremely so. In so many aspects. Well, obviously, with the increasing climate change, it becomes harder to predict kind of patterns of how ground freezes, how deep it freezes, etc. So that's very unpredictable. For example, last winter was very mild. So from my field measurements, personally, we got some very unexpected results, but because the ground didn't freeze as deep as we were expecting. But also Tarun and also me were having a lot of trouble with the understanding and predicting snowfall and cover and how it's distributed by wind.
Because snow changes. As soon as snow lands on the ground, it changes its properties. And even after 30 minutes, you can see that snow has completely, this microstructure has completely changed. And especially in some days when it's rainy and snowing. So what can you expect what's happening under the ground? So this is what makes us difficult. I mean, okay, what we can do in that situation. And this sudden period of summer and winter, like some days are -4 and then it's again coming to 0 degrees for next 3-4 days. Yeah.
And even such simple things as solar radiation, like for example, in the spring when roads are melting, depending on the orientation, one side of the road can melt 2 weeks before the other side. So that side settles because it loses this added strength of the ice, but the other side stays higher. So we get even more like damages and unevenness.
Thank you. I have a question for you. Have you tried working with any types of materials that mimic the same properties as the frozen ground that you were talking about, the permafrost? So like man-made property or man-made materials?
There is no real need for that because we have so much soil that are available. However, what is like the difficulty with soil is that I think when we think about soil or sand, we imagine this very homogeneous material. However, what we're dealing with when you think about roads, like the area that the soil encompasses is so large, but you maybe have like a sample this big. So it's very hard to extrapolate then from a small sample to this really massive area. So but there are some other applications in soil where you model soil as a different type of shape particle to simplify, because again, like there's so many sizes and shapes that you need to simplify the problem to really study it better. So in that sense, we can sometimes work with man-made materials.
That's more like modeling.
Okay.
basically. Yeah.
All right. We have another question from the audience.
Yeah.
Are there like external freezing systems to maybe be able to cause the kind of freezing you have for the piping systems you talked about and culverts?
Okay.
To be able to maybe do an underground tunnel, and if those kind of systems exist, could they be used in, I don't know, could they be replicated in temperate regions where you don't have snow, like places in Africa and all of that? Is it possible to use those systems, replicate it there to be able to build tunnels using that whole freezing?
Okay. I'm not sure if you heard the question. I think you probably did not. What she's asking is whether or not there is some external freezing systems that can be used in other countries where it's not cold. For example, in Africa, in African countries where it's warm.
Yes, that was the purpose of artificial freezing.
But also,
If you remember this digging tunnel which Karina showed,
Mhm.
so in some, I mean, even in India, we use the tunnels underground, but then we need so much because then you need the supply of nitrogen, which makes the ground constant supply. I mean, it stays cooler. This is just that it becomes expensive and expensive. So we have to think about cost here.
There are also some like systems that are not freezing, but cooling, like there are like these pipes I talked about. So there are, because the soil temperature underground is constant and stable and colder than the temperature outside. So there are systems where pipes are buried underground, and then due to natural ventilation, the air is sucked into the pipe and goes through this pipe underground and then comes up inside the house. So the air is slightly colder. And that is one of the things that is like also researched to decrease the amount of air conditioning we need in these warmer countries.
Okay, thank you. All right, well, we're out of time. Let's give a round of applause to Karina and Tarun.
Yeah. Thank
Thank you
you.
very much.
Thank you.
Have a good day.
Yeah.
And we should have Björn on online as well, and he should be coming up with his camera and his presentation. Hello.
Can you hear me, Heather?
Yes, I can hear you. Thank you.
Great.
How are you today?
I am doing quite fine. I hope to bring you a nice presentation today about robotics.
Yeah, I'm sure you will. Well, the floor is yours. Please go ahead.
Thank you. Let me share. Can you see my screen?
We can, yes. Thank you.
All right, great. Then I'll go ahead. So hello, everyone, and thank you for joining me on this presentation entitled Autonomous Field Robots. I am part of so my name is Björn Lindqvist. I am part of the Robotics and Artificial Intelligence team at Luleå University of Technology. And the overall research subject that we're working on is autonomy, meaning self-driving, self-flying, self-controlling vehicles. And we also have a great focus on, as we say in this title, on applying those autonomous solutions in the field, meaning we apply it on real solutions out in the world. We are a relatively young team here at Luleå University of Technology, but we've seen a lot of rapid growth in the last years. Robotics is a very, very hot topic right now. Even to the point where this slide is quite outdated. And at this point, I believe we are around 25 people in the team right now. And this is not really important, but just want to mention that as we do have a very strong field application point of view in our research, we have very strong collaborations with multiple international and national companies, notably the mining industry here in northern Sweden, like LKAB, Boliden, and such, and also with Luleå Energy and Telia. We also have a strong collaboration with NASA in terms of space robotics and autonomous solutions in space, which I'll talk a little bit more about later. All right. So more specifically, what do we actually work on in our team? You can see that we have two general main directions of research, that being inspection robotics and search and rescue robotics as the two overarching themes. But the thing that unites those two things is that generally we want to send in autonomous robots to perform different kinds of object detection or inspection missions in dangerous areas where you do not want to send in humans. But at the current stage, that's the only solution. So some examples of that would be inspection of wind turbines, inspection of power lines, and in general, very hard to reach in dangerous places, such as when there's a forest fire and you have to monitor where the forest fire spreads, search and rescue situations when there have been avalanches, and for example, inspecting nuclear reactors and such for damage. We are also working on sustainability and efficiency in the mining industry. Again, generally on the inspection robotics side, where our job is to design autonomous robots that can perform inspection, 3D reconstruction, and such tasks in the subterranean mining environments. Yes, and we're also working with general support robotics and medical assistance, and as I said, search and rescue robotics is a big one. We are trying to also start a lot of collaborations with the fire departments and police departments and such to really push the utilization of robots in search and rescue and dangerous missions. We also have a very interesting new application, that being space robotics. I do apologize for the images being a little bit low quality here. We have a close collaboration with the Karina space section and also with the Jet Propulsion Laboratory of NASA. And the overall goal is to increase autonomy and intelligence in robotics applications. So for example, you all know that we send large rovers to the moon, to Mars, to different planets. And these robots are great, but they're not very intelligent and they're not very capable of performing complex tasks and complex missions. So we want to develop artificial intelligence and autonomy solutions that we can embed on these robotic platforms, such that we can perform much more complex tasks, such as space debris cleanup, autonomous space debris cleanup, and for example, the search for extraterrestrial life in, for example, lava tubes on Mars or other underground areas where the robots would be unable to be communicated with from Earth or from any satellite in orbit. So in those missions, it's absolutely crucial to have a completely autonomous robot performing the task. Anyway, so I've been talking a lot about artificial intelligence, autonomy. But in my opinion, there's a lot of misunderstanding or simplification of what we mean when we talk about artificial intelligence specifically. A lot of people have this kind of Westworld or general sci-fi notation of artificial intelligence, where we instantly see this human-like entity that's capable of talking, and it's generally trying to mimic human behavior. But that's not really the case in AI. That's just a very small part of it. What we're working with is the ability for a robot to perceive its environment based on sensors on board the robot, make a decision based on the information that it has gathered, and then translate that into actions interacting with the environment as to complete its overall complex task, like for example, producing a 3D reconstruction of a completely unknown structure. So in robotics, a very general workflow that you will see in this kind of autonomy solutions is that a robot carries sensors that produces different perception outputs. This could be a camera stream or a laser scanner and such. Mission planner, which generally answers the question of what we should do and where we should go. Path planning, problems generally dealing with how to get there. And then the control layer, Geotechnical, which is generally the background that we all have in robotics, is trying to answer questions of how to move the robot. For example, a walking robot has a very complex control system to just be able to walk. Right, yeah, so with the general idea that autonomous robots should complete complex tasks while online using onboard sensors on the robots to interact with their environment to complete the task. We are also part of the Darpa Subterranean challenge, or the Darpa Robotics Challenge, which is the largest robotics competition in the world. We are one of only 2 European universities who are attending, DARPA in this case being the research department of the American Defense. This is a very major research competition with a lot of huge universities and industries participating. And the general goal here is to have multiple autonomous robots moving through vast, very large subterranean structures with a mission to locate objects, produce 3D maps of the environment, and in general move through very complex and dangerous areas. And this with the overall motivation of being able to advance this sort of autonomy technology in the world to be able to apply it in real search and rescue operation in, for example, metro stations or mining industries or caves, and in general areas where if there has been an accident, if there is a fire, if there has been an earthquake, you really do not want to send in humans before you know what the area looks like. And we were picked up by the Jet Propulsion Laboratory of NASA to be part of their team in this competition. The rest of the team is Caltech and MIT in the US, and then KAIST, which is a South Korean university. And of course, NASA in general is not really interested in search and rescue robotics on Earth, but they are very interested in being able to send robots to other planets to explore underground or subterranean areas there. So this is more of a hype video from our team. The team is called CoStar, and here you can see the partners: JPL, Caltech, MIT, KAIST, and Luleå University of Technology. And I would like to also mention that this competition has been running for around 3 to 4 years, and actually today, in a few hours, the final day of competition is starting. So after today or after tomorrow, we will have a winner in this huge competition with a price of, I believe, $5 million or something like that. And here you can see, a great example of when we're talking about real autonomy solutions. I think a lot of you recognize this this robot dog, which is called Spot, made by Boston Dynamics. It's seen some viral fame in the last years. But Spot, while it's a mechanical miracle, really, it's a great working robot, it's not a very smart robot. It's just a very advanced toy. So what we're working with is what you place on top of it. This is the set or kit of different kinds of sensors, batteries, large computational devices, or powerful computers that can produce the autonomous behavior that we are after. And it is this kit on top that we are actually actively working with. We're talking about sensors, algorithms that control the robot and such. So in this case, this is one of the practice runs from the second competition, which our team won. This is at a high school, I believe, but the final round of competition where this was from was specifically about exploring a ex-nuclear reactor, so a nuclear reactor that wasn't operating anymore. Yes. Anyway, I think we will we'll move on. You can see this is the kind of maps that we produce with this sort of solutions, where we have various communication links and we produce a 3D reconstruction of the environment. All right. So let's move on to some various projects that we have been working with or in our team the last years. This was one of the first major European projects that we worked on. This was before my time here at the Robotics and AI team. This project was about aerial inspection of large infrastructure, in particular wind turbines. Now, these wind turbines are absolutely massive. I think it's something around 120 meters at the top of the top blade. And the only way to actually perform this sort of inspection right now is to, especially on the blades, is to take them down and put them on the ground, because there's no safe way for a human to get up there and perform inspection. So what we developed was autonomous solutions that allowed multiple, in this case you will soon see 2 drones collaboratively perform a visual inspection of the whole infrastructure. And I believe this was the first ever large-scale multi-UAV inspection of infrastructure. So here you can see, I think this is still overlaying one of the UAVs, I think you will see later, but we are producing kind of inspection paths that the UAVs are tasked to follow, such that they inspect the whole infrastructure. And a great thing about doing autonomous solutions instead of having an operator or a pilot drive these drones. This 3D reconstruction is not very dense that you can see here, but that was not really the point. We were talking about close-up inspection of damages, so it's not really visible. But the great thing about autonomous solutions is that they're very repeatable. You can, you could send the exact 2 drones 3 months later, and they would follow the exact same inspection path, and you would get the exact same output. All right, so moving from the very large outdoor infrastructure down into the mining environment. One of the major things that we've been working with, in the last years has been inspection and 3D reconstruction of subterranean environments and mining environments, in particular mining tunnels. So this is from our test site very close to the university. This is under Mjölketsberget here in Luleå, and it's been in general our test site for before we go into the real mines with LKAB and such. This is the closest we can get to testing our solutions in the field. And of course, give me a second, do a little update. Let's see if he wants to play. Spoilers, we have a spot. All right, here we go. So in this case, we're talking about a completely autonomous drone that we send into these sort of tunnel environments. And based on the onboard sensors, we can produce this sort of very dense, very good 3D reconstructions. And these are not just visually looking like this. You could actually load these into a virtual world or a virtual environment, and you can walk through them. So every single point that you see in this image has a like XYZ coordinate to it. And you can see to the right that the robot is actually building a map of its environment while it's moving through it. So this is not based on any kind of post-processing. This is happening online, only using onboard computation of the robot while it's exploring. Another example of a very important concept in robotics is collision avoidance. Here you can see just a short video of our autonomous drone avoiding some obstacles in the mining environment. And yes, this has been the robotic system that I've been personally working on for the last 1 year, around one and a half years maybe. So we're talking about what we call a multimodality robot, which is just a fancy word for saying that we've combined a legged robot, that being the Boston Dynamics spot again. You can see we have our Luleå University of Technology logo on it. So we have combined the Boston Dynamics spot with our own custom sensor suit on top. And we've also made it the carrier for a autonomous drone platform, meaning that one of the largest constraints with using autonomous drones for these sort of missions is that you have to carry so much payload in terms of large sensors and computers that you have very, very limited flight time. But the constraining part about the legged robots or even wheeled robots like ground robots is that whenever there's some vertical displacement of the terrain, like a drop or a cliff, or if there's just a bunch of rubble on the ground or a very small tight passage, then they are completely unable to go into those areas. So what we are working very intensely on is these sort of multimodality solutions where we can send in the legged robot, it carries the drone, and whenever it detects an area where itself can no longer go, we send in the drone to perform the detailed inspection of that area. So I will just show you another video. You will recognize the area since we really only have one of these test sites. I do think I will have to reload again because this does not want to work. Here we go. So again, this is in the test site below Mjölkensberget. And I want to stress that specifically for this mission, it does look like there are a lot of people involved. But from the operator side, we really just press one button, and that is start. And the complete rest of the mission is handled completely autonomously by the robots. You will see a safety pilot following the robots, but he is not interacting with them in any way. So this is the kind of complete missions, complete inspection missions that we're working with in our lab. So the legged robot navigates to a selected deployment point for our drone completely autonomously, while it's producing a 3D map of its environment. And once it reaches the point, it starts to align itself to the tunnel, getting ready for deployment. And again, this mission, I would say, is a pure textbook search and rescue mission. Go into the dangerous subterranean area and then launch the drone into the tunnel, where it will try to detect a set of objects like a survivor and a backpack and such. So this would be something that a search and rescue or first responders would send in to get a general view of the area, where the output would be the full 3D reconstruction of the environment, as well as the location of any objects of interest within it. So you can see the drone performing its inspection mission. And here you can see a hard hat down to the bottom left. And we get a detection hit based on some neural network algorithms that we train to detect these kinds of objects of interest based on the onboard camera. There's a backpack on the top left and some rope on the bottom right that we're also detecting. And then most importantly, the survivor here, the doll that we hid behind a wheelbarrow here. But our algorithms are still able to detect that there was a human in this area. And soon you will see actually the most important part about this sort of mission structure here. You can see that we're actually locating these objects in the environment. So if this was a real search and rescue mission, the first responders who would have to go into this area to save the survivor, for example, would know exactly how the environment looks after the disaster, and also the exact locations in that map of any survivors or objects of interest. Come on. Yeah, again. So this was our general contribution to the general subterranean challenge environment. The ability to send in the legged robots to a deployment point, and then the drone would go in and detect various objects of interest. You can see this is a rather accurate but not very dense map of the environment. But it shows the general structure. All right, so moving on a bit, we're not actually only working with drones or UAV, unmanned aerial vehicles. We also have a lot of other robots that we're working with. This is a Vortex robot prototype, a climbing robot designed for inspection of, for example, different kinds of composite material surfaces like airplanes and such. So this is one of the few climbing robots in the world that can actually climb outside of magnetic surfaces generally you solve this sort of climbing problems by magnetizing the wheels. But our platform can move from surface to surface, go in any direction, and go over from one material to the next. Here you can see it almost looks faked, in my opinion, when you're seeing it in the real environment performing its task. And this was in collaboration with another university, where our task was to design the robot itself and do the mathematics and modeling to enable this huge fan, this electric fan, to perform the suction force that keeps the robot stable on the surface. While the other university's task was to develop the sensors that could detect, for example, micro cracks in this airplane composite material. And the idea would be to launch multiple of those to perform a airplane inspection considerably much quicker than it can be done by humans today. And I guess I would like to wrap up this presentation by by being a bit selfish and just showing you some of the research that I'm working on, that I've had the pleasure to directly work on as my own personal research in the last couple of years. So while I was part of the kind of full missions, I am generally working specifically on navigation and obstacle avoidance. So this is some algorithms that we developed that to the top right, you can see how the drone perceives the world. And this is based on 2D LiDAR scans. And it classifies these, based on the LiDAR scans, it classifies the environment into different types of obstacles. And then we have a collision avoidance or navigation algorithm that plans its path a few seconds into the future and generally trying to avoid these kinds of obstacles. So you can see this white snaking line is how the robot predicts that it will move in the future. And as you can see, very smoothly avoids any obstacles in the environment and makes its way through. And one of the main benefits of this sort of algorithm is the ability to move through very tight openings. So here we said that the drone is not allowed to go more than or less than 0.4 meters from any obstacle in the environment. And we made a small opening of 0.85 meters, being that there's only a 5 centimeter opening from the drone perspective in this case. These slides, what are you gonna do? Here we go. And still based on our autonomy solutions and a very sharp turn, the robot manages to pass through without hitting the propellers into any part of the environment. We also apply this sort of collision avoidance scheme to let's skip the math part. Right. We also apply this sort of collision avoidance solutions to multi-agent systems. So in this case, the demonstration is about small drones avoiding each other inside our lab. And here they are sharing all the information about where they are planning to go. And then they are using this shared information to detect if there's any possible collisions in the path. And if there are, those two robots couple with each other and they decide which paths they can take that satisfy both their demands, so to speak, while still not colliding with each other. Again, to the bottom right, you see how the drone would see the world in this case. So here's a more challenging scenario in this case. We have 10 drones as 2 teams of 5. We task the 2 teams to swap position, and then they should all maintain a specified safety distance from each other. You can see here in the slow motion shot how this sort of obstacle detection based on the shared data is happening. To the right, you see a blue line. That's the drone we're considering, the agent we're considering. And the red ones are the ones on a potential collision course with it, and how they are kind of orchestrating all of their combined trajectories to avoid any obstacles. Yeah, finally, last experiment here. We also introduce a manually controlled UAV where we have absolutely no idea how it's planning to move. So this is just a normal drone controlled by a radio controller, and we're trying to fly it into these drones. We're trying to fly it into the drones that are holding a very tight formation. And as you can see, they always choose these avoidance paths that don't disrupt the other drones, and also avoid the manually controlled UAV at the same time. So we would call this a distributed solution, where each agent is doing its own thing, but they share information with each other. Anyway, I think that's pretty much it for me. I think a lot of other people, so here's some links if you want. Some other people, I'll stop sharing. Some other people talked about what they're doing in their free time and such. So I guess I'll do that on the fly. So I'll just say I started as a university student here at Luleå University of Technology. I did my master's thesis in the robotics lab, and then I right away got my PhD position there. So it was a very straight path into the world of robotics for me. In my free time, I'm generally trying to not do so much technology and such. So I do a lot of hiking. I play a lot of tabletop games, tabletop RPGs with my friends, and I have with me.
Wait for it.
My tiny dog, my pandemic puppy.
No, what's
that
its name?
That I spend a lot of time with.
What's the name of your doggie?
She's called Lila. So
Lila.
In
no, what a sweetheart. Okay, well, I wonder if we have any questions for Björn. Nothing from the audience, but we do in the chat. And the question is this: robotic lawnmowers and robotic vacuum cleaners are things that we're used to nowadays. What do you think will be the next step in home robotics in the future?
So specifically about home robotics?
Yeah.
All right. I think a lot of general assistance robots is one of the next steps.
Okay.
We've had some projects with, for example, Honda in Japan, who are trying to develop these sort of robots that both can. So first step is always like targeted group things. So very elderly people who can't manage on their own, and for example, people with various disabilities or such that are incapable of living comfortably on their own. So we're developing these sort of service robots that can perform simple tasks like picking up objects, carrying objects around, helping out generally around the home. I think that's one of the, if we're talking in the home kind of things, those are one of the most major solutions. And there's not, it is of course on the like autonomy side as well, but it's also about the public acceptance. Like there's a surprising amount of work to like make robots have nice expressions, like looking happy or looking surprised and things like this to kind of get the mind-mind connection with people when you're working in close interactions with robots.
Yeah, I noticed Spot didn't have a face.
No,
example.
It does not have a face. We're not so much on that side when we're doing our field robotics in the mines. They don't care so much about expressions.
No, but it seems like very interesting and important work that you're doing for search and rescue in the mines, which I think, I wish we didn't need to have them, but I think it is very important that we do. So
yes,
very happy that you're working on those kinds of projects. All right, well, thank you very much for today.
Yes,
we can give Björn a round of applause. And we want to, of course, wish you the best of luck in the competition that is today. When will you find the results?
I don't know, actually. I have not been. We have quite a lot of, September is one of the worst deadline months in academia. So while the pandemic did unfortunately prevent us from going to the US in Kentucky, where the competition is held. So we're really trying to follow it online, but I don't know for sure. I think tomorrow morning probably we'll know the the final score. Unfortunately, our team did not perform very well in the earlier rounds. We had a little accident where a drone crashed, and then they had a spot robot basically walk on top of the crashed drone inside the area. So we're keeping our fingers crossed. I mean, we were the drone side of the team, but we're not able to be there. So we're hoping they'll do good without us.
Yeah. Okay. Well, best of luck with that.
Thank you.
Thank you. So since our student ambassadors couldn't be here today, I thought I would share a little bit about the university. One moment. All right. So we are Scandinavia's northernmost university of technology, and we have 4 campuses, in fact. We have Luleå, Piteå, Skellefteå, and Kiruna. And we are a research-heavy university, which means that a lot of our professors work in research, and that means that they have the most up-to-date information on all the various research topics that they're working on. We have 17,200 students, and most of them come from outside of Norrbotten. And that means that while everyone is coming here as a new student, a lot of people are looking to make new friends, which makes for the campus a very open and welcoming environment for everyone. And because we are a small university, often our professors have an open door policy where you get a chance to spend one-on-one time with your professors and get to know them and get to know their research as well. Another one of our strengths is that we work in very close collaboration with the business community. So as a student, you get a chance to work very closely and get to meet your perhaps potential future employers while you're still studying. And this can be through thesis projects, through casework, or just meeting companies when they come here to present. And finally, we have 200 partner universities in 50 countries around the world, which gives you a lot of opportunities for exchange studies. And now exchange studies is definitely something that employers are looking for in the future, because they want to have people who have been abroad and have experienced a different world, or the rest of the world, let's say. So let's watch this short video.
Below zero. Above the clouds. Below the ground. From earth to raw materials. Through fire to construction. To sustainable living. From climate change to changing our way of life. From ideas to humanities to business. From Luleå University of Technology to the world. To the Arctic. Into the future. Into the unknown.
I always get goosebumps when I watch that video. So inspiring. So here at Luleå University of Technology, we have 100 different programs. And some of the areas that you can study are business and finance, nursing and health sciences, acting and different music programs, including jazz and orchestral, teacher education, media and industrial design, and of course our engineering programs, with some exciting programs like space technology and our newest program, or one of the newest programs, applied artificial intelligence, which goes maybe a little hand in hand with what Björn is working on. Here we have a few pictures of what it's like in and around campus. besides studying, there's all kinds of activities that we have available. We have all kinds of different associations, societies, and clubs that you can join. There's clubs in almost anything that you can think of. For example, sports like canoeing, hockey, innebandy, rock climbing, you name it, we have it. And if there isn't anything that is interesting to you, you can always make your own club. And because it's such a welcoming campus, there is always somebody who can join in with your club. If you want to come and visit us at Luleå University of Technology, you can go into this website, Besök oss, where you can come for a campus visit. You should also be able to find the links in the chat. On Tuesday, October 5th, we will be having an open house. It's a digital open house this year, but you can click into that link and hear from some student ambassadors and hear what's going on campus. Every year, we invite high school students to come to test out some of our programs using in this program called mini kurser or mini courses. So in that program, students get their travel paid for by the university and their overnight stay, where they can come in and test out different things. For example, one of the courses, they can make chocolate, and in another course, they get to build a bridge. So really exciting and really a lot of fun. So mini kurser. And Femtech is a similar program. However, it's targeted right towards girls, because we want to have more girls in engineering fields. So we hope that by creating this type of event where they can come and explore and test out new courses, that they will become more and more interested in engineering as a field. So go into that website to find out more. Now, there is those courses will be taking place in what we call vårvinter. And if you don't know Swedish, vårvinter is a term which means spring winter, which is usually around September, March. So it's coming up after the new year. So registration for that will open in November. So that's all we have for today. I hope that you have enjoyed Researchers Week, and especially here Researchers Night, which is Friday today, here at Teknikens Hus. If you live close to Luleå, you are invited to come to Teknikens Hus tomorrow for one last event, which is from 12 to 1 o'clock, where you can meet with Björn and also another researcher from earlier this week, Jan Frostevari, and they will show you both the robotics and 3D printing in metal. So that should be also very interesting. Now, we would like to hear your feedback. So if you go into these links, if you're a student or someone in the audience, you can go to the left link. If you are a teacher, you go into the right link, and there you can give us your feedback on how you found this event. And you even get a chance to win 200 Swedish crowns. So we do appreciate your feedback, because we hope that we can make this event better and better year after year. So on behalf of all of us at Teknikens Hus and Luleå University of Technology, I would like to thank you for your attention here this week. And I would also like to invite you to come and visit us at the university and at Teknikens Hus. Bye for now.